Good morning once again, everybody. We do see a few more people just now coming in. So if you might pardon us delaying another minute or two, we'll go ahead and get started immediately after that. Thank you. All right, good morning, everybody. I haven't seen the attendees number jump in the last 30 seconds, so I'm going to go ahead and get started here. Welcome to the second of 5 short webinars Ozen Engineering is offering on electronics reliability. My name is Glenn Compton, and I am joined later in this presentation by one of our senior mechanical engineer consultants, Dr. Ahmed Algador. So electronic systems are found in nearly all industries, and ensuring these systems remain operational and perform their intended function in a variety of environments is critical to product success and customer satisfaction. Companies who properly address electronics reliability concerns through simulation can meet many of the objectives stated here. Traditionally, companies have used a design, build, test, break, and then fix design cycle. As I'm sure you know, this approach can be expensive and time-consuming. The design rules and best practices associated with this process may not provide engineers with enough guidance to properly design modern, cutting-edge products. By using simulation, virtual prototypes can be created and tested virtually. This provides engineers with a higher degree of confidence that the eventual physical tests they do run will be successful. Performance, safety, and cost are all critical considerations in the design of electronic systems. Devices are required to reliably perform their intended function in a wide variety of demanding environments. If electronic systems get too hot or have a mechanical failure, they may not be able to perform their intended function. In some instances, this could put people at risk. A wide range of customers have benefited from ANSYS electronics reliability solutions. Benefits typically include reduced design development and material costs, reduced product development timelines, and improved product performance and reliability. Engineers must address a wide variety of design requirements when designing electronic systems. These range from electrical to thermal and mechanical considerations. Additionally, products are expected to meet life requirements to ensure they meet their intended function for at least a specified amount of time. Engineers also need to consider the effects of manufacturing, transportation, and product operation as a part of their design process. ANSYS provides a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. Each simulation toolset plays a key role in the understanding of how electronic systems operate and perform in a variety of applications. In this 5-week series, we'll feature each of these areas of focus in a separate webinar. Last week, we discussed electrical simulations to address concerns related to signal and power integrity, EMI, and EMC. Today, we're going to focus on maintaining thermal integrity as an essential part of designing best-in-class electronic systems. Thermal simulations allow engineers to evaluate and optimize cooling strategies and component designs. Using ANSYS tools, users can evaluate thermal performance from the chip die level all the way up to the system data center level. Users can also consider downstream effects such as thermo-mechanical effects as PCB and package warpage and stress. To explore the subject of thermal reliability further, I'd like to introduce Dr. Ahmed Algador. Thank you, Ahmed. I'm going to make you the presenter.
Thank you, Glenn. All right. Do you see my screen now, everyone?
Not yet.
Okay. Here we go.
There you go.
All right.
Yes.
Good morning, everyone. Thanks for joining us today. My name is Ahmed Al-Ghandour. I'm an application engineer at Ozen. Today, I'm going to talk to you about the improving electronics reliability with a focus on the thermal reliability. At the end, if you have any questions, please let us know. So if we talk about the reliability in electronics, we need to understand why this is important, right? We use a lot of electronics nowadays, right? Cell phones, computers, iPads, printers, a lot of tools, right? And all this electronics is based on current moving from one location to another, and this cause elevation in heat, and that's where the problem happened, right? When you have elevated temperature inside one of these electronics, can cause different types of failure, including mechanical failure, including electromigration. It also affects the performance and the robustness of the system, because a lot of materials properties will change when the temperature is higher, and this can cause loss of cost, time, efficiency, and that's why thermal reliability and thermal management in electronics became a significant topic in the last few years. But when we talk about electronics, we know there is different scales. We can focus only on a chip or a die, or we can go up to an IC package, or even more when we talk about board assembly, or even a complete plane, back plane assembly, system level, or the highest level, which is a server room or data center. With ANSYS tools, we can do thermal management and perform thermal reliability on all these levels, regardless of the scale. And that's what we are going to cover today. If we start with a chip, which is the smallest component, chip power is a temperature dependent, right? And then that will cause an issue such as electromigration, which means that the system performance will change. Later on, there might be some mechanical failure as well. And ANSYS provide different tools that we can use for such a challenge, which, for example, we have Red Hawk CTA, or chip thermal analysis software, which we can use it for the chip level, when we can provide chip data and package data and perform a thermal analysis, and then extract this thermal analysis, and then go to ANSYS ISPEC, where we can have a bigger system where this chip is part of that system, or maybe different chips are used. With ANSYS ISPEC, we will provide the thermal analysis on the bigger system, using thermal analysis we got from the smaller system, which is the chip, in this case using Red Hawk. So this coupling between both tools will help us to have a very detailed and very accurate thermal performance. If we move a step higher, we can go to the package, okay? And when it comes to the package, it's very crucial, because it's important to provide the characterization of this package, the different component in a detailed, with detailed information, so we can have the right thermal performance as desired for this packages. And that's where ANSYS ISPEC stands out, because it's a customized software for electronics, in electronics thermal management and cooling, and which we can use to model different packages with a lot of variation in details. For example, we can create a detailed or compact or network thermal models for this IC package. When it comes to network, we can use 2 resistor or a star resistor or a Delphi. Also, ISPEC provide us with a standard test JEDEC for the convection test of the packages. As you can see here on the left, we can have natural convection or a still air chamber JEDEC test, or we can use the forced convection, which is a moving air test that we use to test the performance of the package inside ISPEC, ANSYS ISPEC. So as you can see here, we have a different diagram, shows a detailed temperature distribution on the package, and we can see the detailed component of the package presented here of this BGA package. If we move a higher level, when we go to the PCB, which include the chips, include the IC packages and other component, another challenge will come here, which we have how the effect of this thermal results will affect the mechanical performance of the PCB. Are we going to have some deflection of warpage, or it will be it will stay still in the initial geometry without any deformation? In ANSYS ISPEC, we can provide a detailed information about the PCB, including the vias, including the traces, etc., and that's help us to have a detailed thermal analysis And then we can couple the results coming from ANSYS ISPAC with ANSYS Mechanical for thermal stress analysis, where we can have a detailed performance, results of the performance of the PCB under the thermal load and how it affects the mechanical performance. Also, we can use ANSYS Sherlock, which will be discussed later on, that can also help us for some PCB level of performance. As we can see here, we can also couple ISPAC with ANSYS SI Wave, which will have a smooth coupling between the thermal and electrical analysis. We can see here we move the joule heating distribution between both software, so we can exchange the power map and the thermal results between the two software, which give us a more accurate performance of the PCB. So now we have the chip modeled, the packages modeled, and the PCB modeled, but these are just an assembly inside the complete system, right? So if I have a computer, it have one PCB, maybe even more, right? The smartphone, the projector, the drone, etc. All these systems include internally electronics component, right? So we need to model this, the whole system, to see how this whole system will perform. And that's show us again the strength of ANSYS ISPAC, because ANSYS ISPAC can take variety of MCAD or mechanical CAD or the 3D CAD of the system, and at the same time it take the ECAD, which is the detailed information of the PCBs. ANSYS ISPAC will help us to include both with the highest detail of both MCAD and ECAD, and then we can perform the analysis on the whole system, not just the IC package or the PCB, but the whole system, like what you see here in the different images. We have the motors, we have the projector, we have the hand watch, which very impressive of the capabilities that ANSYS ISPAC can have. Another important issue in this, when we talk about the thermal management and thermal reliability, is the dynamic thermal load. As you know, if you're using a cell phone, for example, when you use it, you can just use it to read the news, but at the same time, maybe you can use it to read, to navigate the location using your GPS while you are hearing music or something. So the variation of the need of the power used will change. And with the change in the power, the change in the temperature will happen as well. And that's why it's important to investigate the effect of this dynamic change in the load temperature, in this case, on the performance of the system over the time. And that's very important if we're going to talk about thermal reliability in electronics, to take in consideration this dynamic thermal change. Then we move to a higher level where we want to model, let's say, a big system of electronics. In this case, you don't really need to model every single details, right? Because you don't want to take time to define a lot of inputs, define a lot of meshes, and then long solution time. And that's where it comes, the capability of using the network, okay, or what's called network modeling, okay? When we use network, we use the main features of each component by defining its resistance, by defining its source of power, without the detailed modeling of each single component. So we will have the same accuracy level of the solution, but on a faster and an easier way to represent the whole system. This network modeling is very useful when it comes to IC package. It can be used for if you're using liquid loop cold plates, heat pipes in the system, external heat exchange, and other components also could be modeled using network, which is a great feature. We have it in ANSYS ISPAC tool. So one thing it's important to mention here is the comprehensive multiphysics. ANSYS have this unique capability of coupling different physics at the same time and benefit from the exchange of results to have the most accurate results, and taking in consideration all the variation of input that might be applied in this particular system of investigation. For example, if I am doing some electromagnetic analysis, I know there is going to be variation in the power, and that will produce heat, right? So I can use this electromagnetics tool to extract this temperature coming from this system due to the power applied, and then provide it to ANSYS ISPAC, and then get more accurate results, and then exchange back and forth the power maps and the temperature maps. So eventually, we take in consideration everything in the system. Another coupling is between ISPAC and mechanical component, right? So if I want to do, as I mentioned, a thermal stress analysis, I can move from ANSYS ISPAC, extract the thermal results, provide it to ANSYS Mechanical, and then get thermal deformation, thermal strain, thermal stresses, and understand how my system will act mechanically according to this applied powers and temperatures. Also, we can use ANSYS Sherlock, which is a unique reliability tool by itself to perform different reliability tests for which, by the way, we can use it for mechanical and thermal reliability tests. But as I'm talking only about thermal here, we can use the results coming from ANSYS ISPAC, provide it to ANSYS Sherlock, and perform a detailed thermal reliability test that will give us information about how long you expect this system to live. If there is going to be a failure, what component will fail first, and other useful information coming from this reliability tool based on the thermal results coming from ANSYS ISPAC. One thing also we can use is we can create what's called ROM, or reduced order model. With ANSYS ISPAC, you can extract this reduced order model, which is basically a system that has the effect of all the components that can be solved in a very short time. And then you can use it inside ANSYS Twin Builder to even build a digital twin of your model. So it's a great advantage we have in ANSYS ISPAC, building a ROM so you can have result in no time. And also you can use it to build a digital twin if needed using ANSYS Twin Builder. So basically, it's important to summarize what I was talking about. Is when we talk about thermal reliability, we want to make sure that we have an accurate thermal models, right? So we want to make sure that we have all the details in the system. So to have that, you need to have a strong tool like ANSYS provide here. We need to include all the MCAD. We need to include all the ECAD. All the material properties need to be well defined. Also, we need to understand the physics so we can decide how much details we want to include, right? Starting from the chip level all the way to a server room or a data center, okay? So we can take in consideration all the different thermal behavior, including electromigration, power throttling, and end user experience to be included also if needed. And as I mentioned, you can couple the different different tools from ANSYS, talking here about ANSYS ISPAC mainly for the thermal analysis, and then we can couple it with a mechanical or Sherlock analysis for reliability tests in the mechanical level, or we can also exchange data with electromagnetics software as well. So as a summary, this is the different tool we have on the right, okay? We can see space claim, mechanical and dyna, Sherlock, ANSYS ISPAC, SI Wave, ANSYS Granta for material, Minerva, OptiSlang, and also ANSYS Twin Builder. So depending on what type of reliability test, you will use one or more of these tools. Today, we're talking about thermal reliability. Our main tool will be ANSYS ISPAC and ANSYS Mechanical. In the coming webinars, we will talk about mechanical reliability, and Sherlock will be included. In this case, we'll have a space claim, mechanical, and Sherlock, which are very strong tools that we can use to test the mechanical reliability which you will learn about in the next webinar. So with that said, I will stop here, and if you have any question, feel free to write it in the chat, or if you can unmute yourself. I wonder if you can unmute yourself, or should I unmute all? Let me unmute all. If you have a question, please raise your hand, and then I can unmute you and listen to your question if you have any. Or you can write in the questions if you want. It's up to you. Okay, I don't see any questions, so let me pass the ball again to Glenn to close this webinar. So Glenn, you are now the presenter.
Okay. Well, thank you, Ahmed. So that concludes the session on thermal reliability. Last week we handled electrical reliability, and next week we're going to cover the mechanical reliability perspective, where we'll talk about shock and vibration and drop. Week after that, we'll go into a more detailed look at comprehensive multiphysics, and we'll end the series with a look at Sherlock on July 7th. To register for these events, go to ozeninc.com and look under our training and events, and you will find them on the calendar. There's several training sessions in there, but you'll also find these short webinars as well on the next 3 Wednesdays. Now, modeled correctly, any of these solutions can become extremely complex. Ozen Engineering is here to help. In addition to providing and supporting ANSYS solutions, we also offer consulting services with specific experience in FEA, CFD, and high and low frequency electromagnetics. We're here to help you get the answers you need through ANSYS simulation modeling. If you have any questions about today's session, please feel free to reach out to us either by email, telephone, or through our website. Thank you for attending, and please remember to register for next week's session on mechanical reliability. We'll stay on for a few more minutes in case anybody wants to lob a question, but that is the end of our presentation. Thank you. Okay, Ahmed, I'm going to stop sharing screen and you can stop recording.
Okay, thank you, everybody. It was a pleasure. Have a great day. Thank you so much. Bye-bye.